Yes. Hello, everybody. Hi, my name is Ayman Salama, and I am the Senior Partner Solution Architect specialized in AI and ML, and I am based in London. And today I'm going to give you a bit like this is a bit different, this is a bit generic. It's more of the history of the large language model. So it's a bit more scientific and it's a bit more towards the scientific papers and the history of it. I'll try not to be too technical, but we will have to touch base in a bit of details. So So this session overview is we're gonna start with the large language model timeline, and then we're gonna be looking at what is inside of the box of large language model, obviously. And then we're gonna dive deep into the large language model, and we will end with the foundational model on Amazon SageMaker. So if we consider what happened in the language model to be a big bang, it started with word embedding in 2013, and it ended up with 2023, in which we had the evolution that we have seen so far with GPT and Bard, and many others, fantastic machine learning models. So the timeline happens at the beginning of 2013, in which we had the first mathematical representation of text to the machine, and that was Word2Vec. And it comes in two flavor, bag of words and skipgram. We're gonna see a bit of like what is that. And then later in 2014, GloVe is another fantastic model that was developed as well. And then with the evolution of neural networks, there started to be several application of sequence to sequence, which is on RNN and CNN and even LSTM, and applications on text. And we had started to see decent amount of like generative AI. Sequence to sequence was one of the first. So, and it had some kind of decent accuracy. It was not great, but it did some. It has its own usage. And then everything changed in 2016 when we had the "Attention is all we need, all you need" paper was when it was published. And attention is all you need. It has like a bit of metaphorical here. So attention is all we need as humans. We need attention, but also attention mechanism is all you need is a neural network to be able to have a network that provide long, coherent, generative responses, which we're going to see in details. But attention mechanism was a game changer in 2016. And then after that, we had the first paper publication called ELMO. And ELMO is embedding for large for language models. And it's ELMO, and it's funny because Elmo is similar to the cartoon character Elmo, and it was published. And then a group of scientists in Google in 2018 started to have fun, and they started to generate a model, and they decided to call it BERT, as in Bert and Elmo, the cartoon characters. So we call it the giant gags, which like the big research labs are trying to have fun. And then a bit earlier on that year, the famous generative pre-trained transformer GPT was developed by OpenAI. But at that time, BERT was a game changer. Seriously, like most of the advanced language models was based on BERT. And if you look at the literature, you would know that BERT was cited much more than GPT back then. And then Facebook came in, Meta, and then they decided to release a model called Robust BERT, because BERT is fluffy. So we're going to make a robust BERT, and we call it Roberta. And then we had GPT-2, right? And you see the evolution happens. Started as, I wouldn't say as fun, but I like the idea of research labs trying to call things names and make jokes and entertain the community. So, but jokes aside, that was huge evolution that we have seen in science. And now let me take you into unboxing the generative AI. And let's take one example, which is GPT. It's generative pre-trained transformer. It's a transformer-based model, and you will understand what's a transformer very soon. And transformer architecture was introduced in 2017 in paper produced by Google researcher. And GPT-4 obviously is the latest version that we have of GPT. GPT-2 was developed in 2019, and that was awesome, by the way. Whoever was in the scientific community back then, they knew that that was awesome. The input documents or input data set that is used for training GPT-2 was just a sequence of words, and all what it needs to do is predict the next token. That's it. And its model is a stack of what we call it causal transformer blocks with masked self-attention and use position embeddings. And we have like one slide per each of those names, so we would know. The size of it, as we mentioned in the lab, during the lab, was 1.5 billion parameters. And back then it took 7 days to train it on a 256 TPU cores. That was huge and very expensive back then. The training documents is a lot of people confuse it as that it has used Reddit data, but no, they have looked into the web links from Reddit. However, has more than 3+ upvotes. They collected 45 million links, and that ended up with 8 million documents, 40 gigabytes, as we mentioned earlier in the lab. Wikipedia was excluded because it was used for evaluation, and the input data is sequence of continuous words and predict the next word, and that's it. So it predict the next word. A huge fuzz happened in 2019. Everybody was like, wow, this is a breakthrough in science, which was somehow yes. And the main reason was it has what we call it long range coherence. And basically when you ask it to tell a story, at the end of a story, it will be coherent. It will retain the character names for a longer story. So that's what we call it, a long range coherence. And it had a lot of media coverage. OpenAI was responsible. They schedule a 6-month release, and they have an AI safety researcher to look after the safety of the model. And then they slowly started to increase the size of the model and increase it to publish the model to the public. And then we have GPT-3. And let's just have just a bit of a comparison. What's GPT-2 comparison to GPT-3? If one parameter is 1 second, so GPT-2 has 1.5 billion parameters, and that's in time 47 years if the one parameter is 1 second. So if GPT-2 is 47 years parameters, GPT-3 is 4,449 years. So you can see the difference, because a lot of people, they don't see the difference between 1.5 and 175 billion. It's a huge amount of parameters. And we're going to see at the end of the slides when we wanted to say why the size matters in terms of machine learning models. And we will see very good scientific researches that back this theory. So the cost estimated, but this is just cost estimation, and nobody know for sure. If GPT-2 cost about 100K US dollar to train it, GPT-3 took 4 to 5 million dollar to train it, and that's why it makes it almost impossible for the medium size or small size enterprises to own one of those. So GPT-3 has a breakthrough, obviously, in science, and what makes it really good is what we call it few-shot learning. And few-shot learning, you can say a sentence in English and you give it the French translation, and you make it again and again. That's a few shots. Each one of them is a shot. So you give it a couple of examples, and then you say to cheese, and then you wait for the response from GPT-3. So it will learn what you wanted, what is your question here. And that's different than in Instruct-GPT, ChatGPT, in which you give it an instruction, in which say translate this to that, summarize, extend, expand, respond, check grammar, in which you give it an actual instruction. That's a different thing, and that's a different publication called Instruct-GPT. But GPT-3 needs a prompt, and this prompt you need to give it a couple of examples in which it gives you an output. And GPT is not a ChatGPT. Right, so now let's dive deep a little bit. So I just wanted to touch base on a couple of the common knowledge in which people have around the generative AI. So, and now we're gonna go back in time and start from 1, which is text to numbers. So, and what's text to numbers? Text to numbers is ideally when you have a corpus of many words like Rome, Paris, Italy, France. What we do is we make a vector, all of it is zeros, and we just give 1 when we wanted to say Rome. And that bit is responsible for Rome. And we do the same thing for Paris. We assign the second bit to Paris, and we do the same thing over and over again. And that's fine. So now we converted the text into numbers, and computer can process it, but it doesn't capture any meaning. It's just ones and zeros. So now we wanted to capture context. And this is where the Word2Vec came in place. And if we have a sentence says, hope can set you free, and all what we need to do now is we put the word hope here and give it this hot encoding, the 1 and zeros, as we mentioned. And then we have the set and zeros and 1 zeros. So you can see we have taken hope, and then we take can and put can at the end, and take set and we put it here. So hope set, and then we ask the model basically to predict that we wanted to learn that the word in between is can. And this orange box is a sliding window, and we keep moving it to keep pushing the data to the Word2Vec models. What happens when we do that? The layer in between is the layer in which we can gain the traction. This is the embedding layer. Those are numerical numbers that represents the word hope and can set you free, each one of those words. And we're going to see how it looks like in a second. So you would see that instead of like cat was 1 0 0 0 zeros and kitten 0 1 0 0 0, when we pass it through the neural network, you will see numbers 0, 0.6, 0.9, and so on. And those numbers are learned from the neural network. Those are the actual gradient, the actual weight within the network itself. And when we put this on a 2D diagram, so we reduce its dimensionality, we will see that cat and kitten get closer together and away from dog. And we can make a lot of arithmetics, and this is a very well-known arithmetics, which is we can say this man and woman and king and queen. If we say man plus woman minus king as vectors, the response, the output will be a vector of queen. That was mind-blowing back then, because basically the mathematical vectors retain a meaning, and you can see that representation in multi-dimensions. So that it captures meanings and content, but it does not capture the sequence, and hence the word bag of words, as if like you have taken all the words and you put it in a plastic bag. So now let's have a sequence. We wanted to capture the sequence of the words so we would understand. So we have on the left-hand side the RNN and the right-hand side the CNN. And the RNN basically takes into the account, instead of like input and output, you will take the previous output as a part of the input. Can you see, take the previous output and you pass it to the input. But it's sequential. Sequential is boring and slow. So if you want to train it, a lot of cases it won't converge. So the model, you will have some accuracy, but not the best. CNN, on the other hand, which was used for images, it has proven to be really good with text. And you can take all of the inputs and push it to one output, but then it ran out of memory. So you cannot use it for a very super long memory. So CNN is good, but it has finite memory. So it captured the sequence, yes, but it's either slow or limited by memory. And of course, before we jump into attention, We had the LSTM, which used to be a fantastic solution, long short-term memory, which is an enhanced RNN. It used to be amazing back then, like a couple of years back. And then we have attention, and attention is all you need. And the whole idea of the attention is if you have input like x1, x2, x3, which are like words into sentence, all what you need to do is you take each one of those input and you multiply it by the designated input that you, if you are focusing on x3, for example, you take x3 multiplied by x2 as vectors, and we multiply by the weights, and we take the output and push it to a y3. And we do the same thing with x3 and x3, x3 and x4, x3 and x5, and so on. So, and this means that y3 will have some meaning out of all of the input parameters here. What makes it unique is that this is a matrix dot calculation, and the dot products and the matrix, as you know, with the GPU is super efficient calculation. But let's have a bit of like a meaning, what's going on here and why we care about the that. Someone might say this restaurant was not too terrible. So, and here when whoever said this sentence, they mean that the terrible is a feature property of the restaurants, and not and terrible is inverted, and two is a moderate. So it's like you can see the word terrible by itself contains meaning from restaurants and not and two. So you would want to carry this meaning of terrible with you. So when you want to look at, sorry, it keeps changing the, when you want to look at the image on the right hand side, which is a translation between English and French, and you see the agreement on the European Economic Area will be translated to l'accord sur la zone économique. And you see focus on the European Economic Area to la zone économique européenne. You would see that the, well, let's focus on area and zone. You would see that la zone and the European, so zone becomes European. And look at, if we try to look at the neurons here, if you have the proper attention mechanism, you would see that you can see that the word area and zone had been lightened up in here. And this means that the network was able to understand the correlation between area and the zone, even though in the order, it didn't come in the same order. And this is the one of the breakthrough. So, but when you look at it, it's like super simple, yes, but believe me, before that paper was published, we were like stuck for quite some time in this kind of tasks. So this is where we wanted to see the word terrible, and you would see easily that we have multiplied not and terrible together to push it to terrible. And if you have enough examples, the network will be able to understand that this is a negation, and then it will be able to add this meaning to the mathematical representation of the word terrible out of your own corpus. So obviously, if you have another word terrible in a different corpus, it will have a different position and different meanings because it comes with different context. So the model captured all the words, that's fine, but one attention mechanism is not enough. And then it comes the multi-headed attention. And it's very simple here. If you have one head attention that focus into a simple task, if you have multi-head attention, then you will be able to have multiple attention mechanism focusing on different multiple tasks. So the model here will pay attention to multi-logic, nice, which is a multi-headed attention, but it does not capture the word positions. And now it comes to the positioning encoding. So let's look at two sentences here. This is not a real restaurant, it's a filthy burger joints. And this is not a filthy burger joints, it's a real restaurant. And you can see that the words more or less are the same. Actually, they are exactly the same. But when you shuffle them, you attain completely different meanings. And then here is one of the coolest invention that I like about the transformers. It's the positioning encoding, which is assigning a simple sine or cosine wave to each letter or each word, which will retain its position within the sentence. Some people might use, which I don't like, the Fourier transform analogy, in which you can take an analog signal like sentence, and you break it into a couple of sine and cosine, and those are like position of each word. This analogy might help you to understand how did we use the sine and cosine wave for positions, but it's not entirely right. But at the beginning, it helped me to understand how did they use the positioning encoding. So now you see, we first converted text into numbers, and then we added a neural network to it, make it use Word2Vec, so it retained context. And then we started to look at the sequence by using RNN and CNN. Then we have seen the attention mechanism in 2016 and how it retained a specific function of attention, how we added multi-attention together to have multi-attention heads to the transformers. And then we have seen how they use the positioning encoding, which are sine and cosine sine waves to specific words or letters within the sentence to keep its position. All of that builds up to BERT and GPT. So a transformer block is composed of a layer of normalization, and then a self-attention mechanism, the one that we mentioned, and then another layer of normalization, and then a normal feed forward. And that's what you have here. And of course, you add to it the positioning encoding. So you see the input here to your transformer head, and then you send the output as well to the similar one. But after that, the second multi-head that it has, it will be fed out of the input that comes from here. And then you have like another transformer. So if you look at it, it might look simple. If you see it's just positioning and coding to have the positions, multi-head, normalization, and a simple feed-forward network. And the same thing here, mask it, which we can explain in a bit, multi-head and a normalization, and then take the input from here and here, from the input and output, and push it to, again, another multi-head. And then you have a transformer. It sounds nice, but it works really well, even if it's simple. So BERT, with a successor of Elmo, and it's a single stack of non-causal transformer block, and it retained the positioning encoding. It have a dimension of 1024, 16 heads, as you see, 24 blocks of transformers, and it was just 340 million parameters. That was huge, by the way. It took 64 TPUs, 4 days to finish this training. But now that's like a lame, it's a super small one, which we basically more or less have done it today in our lab. So, and that was trained on 2,500 million words from English Wikipedia and more than 800 million words from book corpus. So masking. A lot of people might find it difficult to find data to train. So we call it the self-supervised train. So we have a sentence and a dog on a skateboard. And what we do is, in order to get like a labeled data set. So we take the word dog and we replace it by the word jealousy, as you can see down here. So the word jealousy, the word jealousy is a wrong word. So we just wanted to tell the network like, hey, if you see a jealousy on a skateboard, it's a wrong thing. And then we take the word A and just mask it, and then later give the network the output as A. So the network will learn that the word jealousy is in the wrong place and the word A, skateboard, is in the right place. So basically make it like a self-supervision technique. And then you add to the last layer classification, saying that this sentence is for this and that. It can be sentiment analysis, it can be classification of documents, types, or so on. So that's the last layer in which you fine-tune your model, your BERT on. And that's how it comes to be one of the fantastic machine learning models back then, BERT. And then we have the autoregressive, which is a network that predict, if you see the word hello on the top and in the below, and it's shifted by one character only, and that's basically it. The input is a sequence and the output is the same sequence but shifted. So we allow the network to learn to predict the next character or the next word. And it's non-causal, and I promise to mention this at some point, because the BERT is a bidirectional. It learns from right and left, so it learns from both directions, and it depends on the future and the past to predict the future. However, here you cannot make it a cheat, so you actually redact one character from the future, so the network will be able to predict it, so it's not non-causal. And then it comes the GPT-3. And it's the same. It's autoregressive language model. It's a stack of causal transformer blocks, positioning encoding, but the size of it is 175 billion parameters in total. So now it comes to the few shots learning by prompt. And some people, so originally, if you have not used, if the first GPT you have used is ChatGPT, in which you give it an instruction, that wasn't the case in GPT. GPT, you need to give it something, and then it will continue doing it. So you start by saying a piece of poem, and then it will finish it up for you. Or here, for the example down here with the poor English and good English input and output, you give it a poor English input and then a good English output, and you give it multiple examples, and this is what we call a few shot. You give it like, hey, learn by this and that. Why this is important? Because you built a generic language model, and we wanted everybody to use. But then, like for the example of BERT, if you wanted to be talking about a specific business banking problem, for example, you would want to fine tune it with maybe 10,000, 20,000 examples, and then you fine tune it. You run the code, you do the whole lot of things, and then you got a new model that is based on a generic language model, but is fine tuned on a specific subtask of classification for business banking. So, and it requires a machine learning engineer to do that and a data scientist, and obviously labeled data set, which is expensive. So the task here is like the scientists were trying to find a model that is able to do that with a few shots. You just give a couple of examples like poor English input, good English output, and you repeat that multiple times. And then the last one, you give it a poor English input, it will give you the good English output on its own. So just learn from 6, 7 examples. And if you look here at the top, zero shot, which basically you just give it one example. Hey, what's 3 plus 5? So, and you see if it's able to do that properly or not. And then you give it one shot. Hey, 1 plus 8 is 9. So please answer 3 plus 5 and see what it's going to do. And then few shots. So look at the graph on the right-hand side. The graph on the right-hand side, on the x-axis, it has the size of the models. And on the left-hand side, it has the accuracy. The y-axis is accuracy, x-axis is the model size. And you can see that the 3 lines, a few shot, 1 shot, and 0 shot, all of them perform really bad when the model is small. And that it changes drastically when the model goes up to 170 billion parameters. And this is what we wanted to say. As scientists at some point of time, they figured out that every time they increase the size of the model, it performs slightly better. So what happens if we make it bigger? And this is how they get a lot of money to start working on large language models. This is another example of, you can see on the y-axis is the accuracy, and on the x-axis is the number of example of by context. And you can see each one of the graphs, the lines, the blue line is 175 billion parameter in comparison to the 13 billion parameter, for example, the orange line. So you can see that the blue line, the big model, performs significantly better than any one of the smaller models, even if all of them are being trained on the same exact data set. So now you see that the hypothesis was very simple. If you have more parameters, there is a tendency that each group of attention mechanism, for example, attention heads, will focus on a specific task on its own. So let's break it down a little bit here. Look at that. Those are a number of different kinds of tasks. arithmetic tasks. And as you might know, GPT is not trained on math at all. And then if you have 1 billion parameter GPT, as in the first graph on the left top hand side, you would see that 1 billion is basically zero. 1 billion parameter model performs zero with arithmetics. But see what's going to happen when you increase this to 100 billion. You see a significant increase on its performance on arithmetics, and it was not trained on arithmetics. And the model basically started to learn specific tasks on its own because it's big enough. So it can dedicate a specific group of neurons for a specific task, or a specific group also of attention heads for a specific task. And this it happens all over the place with questions and answers, word and context, multitask, and so on. And you can see in all those graphs, there was a significant change happens when the model get bigger. And this is the breakthrough. The second breakthrough that was done for the recent model, for example, ChatGPT, using the reinforcement learning from humans, human feedback. And the difference here is that it optimized the language model on the human feedback as a reward signal. So if the model comes back with a response and the human that is actually labeling the data, looking at the response of the model, says, no, that's not right. So they take the feedback and retrain the model again. This kind of reinforcement learning allows the model to behave much more significantly better, closer to the human feedback. And that was another breakthrough as well, because most of the generative AI models prior to the launch of GPT-3 and ChatGPT was you just launch the model and let it say whatever it wanted to say. But the OpenAI have invested some money into bringing people to provide a proper feedback to fine tune the final version of the model. All right, so the Amazon SageMaker foundational model. So what can you do on Amazon SageMaker? So Amazon SageMaker foundational model comes in 3 flavors. The first one, you can have an inference with 0, 1, or few shot learning. And this means that you can get a model, click one click, and you deploy that model. And you have like a single API call. You don't need any infrastructure specified for that. You don't need any data to fine tune the model. But that's fine, but it comes with a cost, which is it's harder to customize for depending on the use case. And it's harder to have a memory context. And let's say it this way. If you have a business use case, business banking use case, can you use a generic language model to answer your customers' questions? You can, but your model might be behaving wrongly. It might answer wrong questions. It might have been learning things about things that you don't want your customer to learn from. Like you don't want it to respond about the weather, for example, because your customer might sue you if your model responded in a wrong way. So it might be good as a productivity tool, but for a business use case, it has to be a very specific generic use case. And if you are using an API call to an existing model hosted on an external company, then you need to check on the privacy policy of your data. Can you actually send your data to a third party and they use it to train the model, and then you use an API calls? For the majority of the cases, it's not right for the majority of the cases. But you might want to, which is the second one on the middle, fine tune and deploy for inference. So it's easy to customize. You can distill, make it smaller, make it lower cost, and you can improve the latency. But this requires from you to get a model, get the infrastructure, get the data, get the people, train the model, and then put the model on your premise, on what, even if it's on the cloud, it's on your own cloud. No one have access to it, so that's yours. And then obviously the best option that you have is reinforcement learning agent to improve the quality. And that you can have a human in the loop to get a feedback, and then you validate the information from humans and reinforce your model to learn from that. And obviously you can have like a user interface with end users to say like, yeah, I like this answer, or I don't like these answers, and so on. But that requires much more developments, and you have an entire life cycle of uh, getting feedback, retrain the model, deploy it, and so on. So right now, as we speak, we have the foundational models on Amazon SageMaker. That allows you to have multiple sets of models, different kinds of models that comes from our third companies such as AI21 Labs, Hugging Face, Stable Diffusion. So, and you have different kinds of models that you can use for different use cases of classification, generating AI instructions, image generation, and so on. And all of them you can use on SageMaker. Obviously, today during the labs, we focused more into getting Hugging Face, focused on to getting GPT-2 code, and then train that model, and hopefully deploy that model on your own infrastructure that you own and nobody have access to it. So, and if you are able to do that, then you have your own generative AI. It might not be the best option in terms of like if you compare it to ChatGPT. Obviously, that's a very expensive model in comparison to much cheaper model, and but it might fit in exactly your needs. And I would suggest that to a lot of the enterprise grade developers to focus more into how to develop their own models and how to deploy their own models on their own infrastructures, on their own cloud accounts, to make sure that you get the maximum use out of it. And obviously, you have the foundational model to make it easy for you with a click of a button to deploy that model in your infrastructure and play with it. So you can see if it fits your business use case or not. So throughout the day today, we had two labs, one on how to use data parallelism and model parallelism, and how to train generative AI model on SageMaker using distributed training. And in this session, we went through very quickly the evolution of large language models, and when did we start from 2013 and all the way up to the breakthroughs that we have at the moment. And we have seen that several contributions from universities and big institutions contribute to the scientific community to build up this. And even if this ways, some people might look at it from the business perspective, it's indeed a very beneficial to the human race, because we evolve much faster now because everybody is contributing, and I'm hope that we will continue to do the same thing for the benefits of the humans. So for that, I would like to thank you so much for your time. I know that it has been long 2 days for the majority of you, and for those who have stayed till now, I would like to thank you so much for your dedication and staying the whole time till the end of the session. And I hope that you have learned something new today. And I open the platform for questions. This is my email address. Please have it. You can also find me on LinkedIn if you want to reach out. If you have questions, if you have business use case, if you just want to have a conversation, I would be more than happy to talk to you and talk to you about your business use cases and how can we help. So for that, I thank you, and I give the mic back to Joe, and I open the platform for questions if there is any.